As we dive into our study of chemistry, it's always good to start at the beginning. So this first unit, the first module, is called the Essentials of Chemistry. And so why not start off with a definition of chemistry? It's defined as the study of matter and the changes that matter undergoes. So digging way back into your filing cabinet there in your brain, find the definition of matter. It's anything that has mass and takes up space or has volume. Okay. So any good scientist knows that to study science, we need to follow the scientific method. There's a lot of different ways of describing this. This is just one of them, but they're all basically the same idea behind the steps. So the first step in becoming a scientist is to make an observation or to look around the world and to pay attention to what's going on and try to figure out why. Why does it happen? What's happening? How is it happening? Those kind of things. So we're going to ask questions. The who, what, when, where, why kind of questions. Okay, be curious. Now, in chemistry, there's a lot of things you may be curious about that you can't study because it's dangerous or because it's, requires equipment that we don't have. But that's where we always start, asking questions. So once we decide what we want to study and we've got an idea of what we're curious about, we formulate a hypothesis. Now, I know you've probably learned that a hypothesis is an educated guess, but it's so much more than that, okay? It's a statement of what you think the relationship is going to be. So typically, a hypothesis needs to be stated: if this is done, then this will happen, okay? So if I change the kind of plant food that I'm using, then the plant will grow taller. That's a hypothesis. Just saying, well, I think that the plant might grow. That's not a hypothesis. That's just a guess. Okay. To test your hypothesis, you're going to have to run experiments. A hypothesis is no good if it's not tested. All right. So for an experiment, this is going to be a set of tests. And of course, the kind of test and the way you go about that is going to depend on what you're studying. But a good experiment needs to have these parts that we're getting ready to talk about. The first is the independent variable. This is the variable that is changed by the scientist that you're trying to study its effect. Okay? So changed by the scientist to study its effect. And then the dependent variable is what you're studying. It's what's being affected by your independent variable. So it changes as a result of the independent variable. So in my really simple case a minute ago with the plant food, the independent variable would be the amount or type or whatever it was I was using for the plant food. And the plant growth would be the dependent variable. So when you're trying to study one particular property or characteristic as a result of one particular other thing, everything else that could have an effect on your dependent variable needs to be held constant. So constants are everything else stays the same. So you isolate just the effect of the independent variable. And so going back to that simple little plant example, if you're trying to study the effect of plant food on plant growth, then you would want the amount of water the plants got, the amount of sunlight the plants got, the kind of soil they were in, everything, the kind of plant it was, everything else would need to be held constant, or else you wouldn't be able to say for absolute sure if the plant food was having an effect on the growth or not. Okay. The control, and now this is one part of an experiment that not all experiments will have. The control is a test run without the independent variable. So you want to see what the natural change in the dependent variable is. And so in my case of the plants, we could definitely have a control. You would just have a plant that was growing with no plant food at all. But the water and the sunlight and everything else would be the same so that you could see how the plant would have grown naturally. Okay? So as you're running these tests, you're going to be collecting data. And data is important because that's what's going to tell you whether your hypothesis is being supported or not. So your data are your measurements. Okay, it's collected during your experiment. And so there's two types of data that you can collect. You can collect quantitative data, which is going to be your numerical measurements: length, width, height, weight, time, temperature, anything that has numbers with it. That's going to be your quantitative data. Where your qualitative data are going to be your physical observations: smell, color, shape, healthiness, anything like that. So in this plant example, your quantitative data would be the time that you're waiting between measurements and the actual measurements themselves. You're using a ruler or yardstick, whatever, to measure the height of the plants. Your qualitative data would be observations on how the plants are looking. Are they turning brown? Are they looking healthy and green? Are the flowers blooming? Whatever like that you're using your senses to make those observations. So once you reach what you decide is the end of your experiment, let's say you were measuring them for 6 months, okay? Then you're going to draw your conclusions. Your conclusions are going to be the analysis of this collected data. And you're looking for, did it support your hypothesis or not? Now, something that we make a mistake about constantly is saying we were proved correct. You can't automatically and exactly say, yes, the plant food made the plants grow more. You can say the hypothesis was supported from the data collected in this experiment. It appears that plant food does have an effect on plant growth. Okay? Because there could be other experiments where the data doesn't come out that way. You would have to have a series of repeated experiments with the same conditions that show the same results. Okay? So, when you have that, then you can get to what we call the scientific theories and the scientific laws. Now, scientific theory is a tricky terminology here because we say it's just a theory a lot of times. A scientific theory, if you look at this definition, is a unifying principle that attempts to explain a body of experimental observations. So, in other words, if someone has run multiple experiments of the same thing, different scientists have run the same experiment and gotten the same results over and over and over, and it's looking like it is confirmed, then we have a scientific theory. And that theory can be used to predict related phenomena. Okay? So it's not just a theory, it's something that has been supported by data for a long period of time. Does that mean it's absolutely correct? Not always, because there can be better experiments, better data later that negates it. Okay? But it is more than this idea of, well, we can just ignore it because it's just a theory. Okay? Scientific laws are concise verbal or mathematical statements of a reliable relationship between phenomena. So, gravity is a scientific law. We know that if we drop something, it will fall down, it won't float up. Gravity is scientific law. All right. It results from a series of consistent results from various experiments. So, this is when we can relate things. We'll talk about gas laws later in the year. And those are mathematical relationships between properties of gases that have been repeatedly shown to be true in multiple experiments. So we will pick up in the next video and talk about some state of matter stuff.